Swayam Prabha. Digital India. Educated India.
Last class we studied basic introduction to the rotor dynamics. We saw the course content. We saw very basic definitions of some of the phenomena which occurs in the rotor dynamics, like whirling, unbalance. In the present lecture, we will continue with those concepts, but we will review some history of the rotor dynamics. So that and during that description of the history, I will be introducing various phenomena which people observed and then they try to analyze. And so this particular module is concerned with the history of rotor dynamics, and this is the outline of the course, in which we have introduction and some basic definitions which we studied earlier. Also we will review that, we will extend the more explanation to those definitions. And in history, I will start with the Rankine, who first analyzed on the rotor analysis, how to obtain the natural frequency of the system. And so this is the first phase, in which Rankine to Jepcot I will review, and then the second stage will be from Skoda to Lund, and the third stage from Dimmenberg till now, what are the developments have been taken place. And so you can able to see that this particular lecture will review early development of simple rotor model, analysis tools, and introduction of various kind of instability in rotor bearing system, because instability is very important in analysis of the rotor bearing system. So let us again see what is the basic definition of a rotor. Rotor is nothing but a body suspended through a set of cylindrical hinges or bearings that allow it to rotate freely about an axis fixed in space. So, this is very abstract definition of the rotor, and various engineering components concerned with the subject of rotor dynamics are rotors of machines, especially turbines, generators, motors, compressors, blowers, and the like. Even in the household applications or medical applications, we will find such rotors. The parts of the machine that do not rotate are referred to with the general definition of stator. And rotors of machines have, while in operation, a great deal of rotational energy and a small amount of vibrational energy, which is actually unwanted for. Main aim should be to have as much as rotational energy and minimum vibrational energy. And you can able to see that it is very evident from the fact that a relatively small turbine propels a huge aircraft. And with this figure, I just want to introduce basic components of a rotor, especially in the in a laboratory. So here is a motor which drives a shaft through a coupling. The shaft is supported on two bearings here. One is bush bearing, other end is the fluid film bearing, and on the shaft there are two heavy discs. The shaft is relatively massless or is flexible, and there is a rigid base generally which is fixed to the heavy foundation. So, this is a very basic components of a rotor system in a laboratory. This is a close view of the disc. Generally we provide some kind of poles in this, so that we can able to provide some kind of unbalance, known unbalance to this, to study the unbalance vibration of the system. Now, let us see a industrial rotor that is also having similar components, but they are having huge size, like you can able to see the bearing here, and a rotor with various stages of the blades, stator, foundation, which will be mounted on a heavy concrete structure. So, you can able to see that the main purpose of the rotor dynamics as a subject is to keep the vibrational energy as small as possible. In operation, rotor undergoes the bending, axial and torsional vibrations, and this is a very schematic of the same, that is a turbine generator set with a coupling in between. And if we have multi-stage turbine, then we can have high, that is high pressure turbine, low pressure turbine, then generator, and all are connected by coupling and supported at various bearings. Even you can able to see the exciter here. So, these all are nothing but rotors which are mounted on bearings. This is another example of a turbo machinery which is generally used in the aircraft, and in this, because of the space constraint, if you see the schematic of this, you can able to see there is a rotor which is mounting a low pressure compressor, and then other end it is mounting the low pressure turbine. This shaft is supported at two bearings, one at this right hand, another extreme left hand, and you can able to see there is another rotor which is concentric with this main rotor, on which there is a HP compressor, this one, and there is a HP turbine here, and they rotate at different speeds and they transmit power. So, you can able to see that because of the space constraint, these two rotors which are concentric and supported at intermediate bearing, they rotate at different speeds. Okay. So, let us begin with a brief history of rotor dynamics. We will start with Rankine, and then till now whatever the developments have been taken place, we will study this. And you can able to observe during the discussion that is already more than 140 years have passed when the Rankine analyzed the rotor system. And so, let us see the history of rotor dynamics. So, rotor dynamics has a remarkable history of development, largely due to interplay between its theory and practice. So, the practice and the theory in this particular subject goes side by side, and rotor dynamics has been driven more by its practice than by its theory. This statement is particularly relevant to the early history of rotor dynamics. Research on this particular rotor dynamics spans for more than 140 decades of history. Rankine in 1869 performed the first analysis of spinning shaft. He chose a 2 degree of freedom model consisted of a rigid mass whirling in a orbit with an elastic spring acting in the radial direction, and he predicted that beyond a certain spin speed, the shaft is considerably bent and whirls around in its bent form. He defined this certain speed as the whirling speed of the shaft, and in fact it can be shown that beyond this whirling speed, the radial deflection of Rankine model increases without limit. So, it goes to unstable region. Today, this speed would be called the threshold speed of divergent instability. However, Rankine did add the term whirling to the rotor dynamics vocabulary. So, whirling first was used by the Rankine. His analysis was having some flaw, as we will see in subsequent slides. So, this is the Rankine model in which he considered a rotor as a mass and supported by a spring. Spring had directional change in the stiffness, and you can able to see that because of this, this particular rotor will be having some orbit depending upon the stiffness of this spring. It can either a circular motion or elliptical motion. If there is a cross coupled terms and asymmetry in the support, it can have elliptical, or in extreme case the elliptical can have a straight line motion. Basically, that is nothing but a single degree of freedom mass system in which that particular model can be analyzed. This is a very basic model of a spring and mass damper system. The damper is not there in this, and this is the external force, maybe due to the unbalance. Okay, so now let us see the whirling. The whirling refers to the moment of the center of mass of the rotor in a plane perpendicular to the shaft. To have more understanding of this, let us see this figure in which this is the bearing axis and this is the shaft which is bent. Now, and this has bent because of is spinning about its own axis at omega, and this bent shaft itself is revolving about the bearing axis, and there is that frequency is nu, that is called whirling frequency. So, you can able to see the whirl motion is nothing but the bent shaft when it revolve about the bearing axis, that motion is called the whirling. The frequency of whirl depends on the stiffness and damping of the rotor, and the amplitude is function of the excitation force, frequency and the magnitude. And there is a concept of critical speed also in the rotors. The critical speed occurs when the excitation frequency, which comes generally because of the unbalance, coincide with the natural frequency and can lead to the excessive vibration amplitudes. In this particular Rankine model, as I pointed out, there was some flaw in his model. So, Rankine's neglect of Corley's acceleration led to the erroneous conclusion that confused engineers for one half century. The turbine built by Parsons in 1884 operated at speed of around 18,000 rpm, which was 50 times faster than the existing reciprocating engines at that time. Actually, the Rankine he predicted that there is a certain speed beyond which the rotor cannot be operated, because it goes into the unstable region and you cannot able to operate the rotor, and that discouraged the industry to design rotors which can operate at very high speed. And Rankine was as such very renowned person, so no one could able to object his predictions. But you can able to see in this that like Parsons, he actually made rotor and they were operating at very high speed. Similarly, in 1883, Swedish engineer D. Lavelle developed a single stage steam turbine, that is impulse turbine, and it is named after him, for a marine application, and succeeded in its operation at 42,000 rpm, which was very high speed at that time. he aimed at self-centering of the disk above the critical speed, a phenomena which he intuitively recognized that was actually contradicting the Rankine's prediction that you cannot able to operate the rotors beyond certain speed. But he was getting in actual test rig self-centering of the rotor when it is operating at above critical speed. That means it was operating at more stable form. He first used the rigid rotor, but later used a flexible rotor and showed that it was possible to operate above critical speed by operating at a rotational speed about 7 times the critical speed. So, that was the real experiments. It thus became recognized that a shaft has several critical speed, and that under certain circumstances these were the same as the natural frequency of a non-rotating shaft. The Dunkerley in 1895 found, as a result of numerous measurements, the relationship known today by that of Southwell, by which the fundamental critical speed can be calculated even for complicated cases. So, this is the first sentence of the Dunkerley's paper, which reads as, it is well known that the average shaft, however nearly balanced, when driven at a particular speed, bends, and unless the amount of deflection be limited, might even break, although at higher speeds the shaft again run true. This particular speed or critical speed depends on the manner in which the shaft is supported, its size and modulus of elasticity, and the sizes, weights and position of any pulley it carries. This was the first time the use of term critical speed for the resonance rotational speed was used, and even with the general knowledge of critical speed, the shaft behavior at any general speed was still unclear, but more was learned from the calculation of unbalanced vibrations as given by the Foppel in 1895. Foppel used an undamped model to show that the unbalanced disk would whirl synchronously with the heavy side flying out when the rotation was subcritical, and with the heavy side flying in when the rotation was supercritical. Also, the behavior of level rotor in 1889 at high speed was confirmed by this theory. Now, let us see through animation what is the synchronous world when the heavy side is flying out and when the heavy side is flying in after at the supercritical region. So, let us see through. Yeah. So, here you can able to see that this is the shaft at which is whirling, this is the bearing center, and the heavy side, that means the where the unbalance is there is outside, and we are considering the synchronous world. Because of that, when it rotates along the orbit, always the heavy side will be outside. You can able to see the spin direction is counterclockwise, also the whirling direction is also counterclockwise in this particular case. So, this is the motion in which heavy side is always outside. The same motion as the earth and moon are having, the moon and earth is at the center, that kind of motion we can have. This once we cross the critical speed, this heavy side comes inside, and you can able to see that always it is inside during the whirling, and this is the animation of that, in which rotor is whirling and generally this will occur when we are operating above the critical speed, and heavy side will be inside all the time, and because of that you can able to see that vibrations will be less because unbalanced force will be toward the bearing axis. This is another kind of motion in which actually this is at the critical speed. At critical speed, this heavy side will be in the direction of motion. So, it will be tangent to the orbit motion, and this, as we know, at critical speed large oscillations take place and the response is increases with time, and this is a dangerous situation. This is another world in which anti-synchronous, that means the spinning of the shaft and the whirling of the shaft directions are different. So, in this particular case the shaft is rotating in the clockwise direction and the whirling direction is counterclockwise direction, this direction. So, in this particular case the heavy side will be coming in and out at every 90 degree. This is the animation of that particular motion. Okay. Now, we will see what was the contradiction between the Dunkerley's calculation of natural frequency and Rankine's model. So, you can able to see that it is regrettable that what Dunkerley's regarded as well known was actually little known. Also, practitioners of that day were not aware of 1895 analysis by the German civil engineer Foppel, who showed that a rotor model exhibited a stable solution above Rankine's whirling speed. We cannot blame them too much, since Foppel published his analysis in a journal which that was probably not well known by contemporary rotor dynamists. More telling was about the apparent indifference to the practical work of Swedish engineer De Level, who in 1889 ran a single stage turbine at supercritical speed. One can speculate that engineers of those days labored under a confusion of concepts, equating Rankine whirling speed. For present day, it is the threshold speed for divergence stability with Dunkerley's critical speed. There was not matching, and people were confused what to do with these two calculations which are not matching. This was particularly unfortunate, since Rankine was far more eminent than Dunkerley, and as a result his dire predictions were widely accepted, even it was erroneous, and became responsible for discouraging the development of high speed rotors for almost 50 years up to 1916. It was in England in 1916 that things came to the end. Kerr published experimental evidence that a second critical speed existed, and it was obvious to all that a second critical speed could only be attained by the safe traversal of the first critical speed. And then the Royal Society of London commissioned Jeffcott to resolve this conflict between Rankine's theory and the practice of Kerr and De Level. The first recorded fundamental theory of rotor dynamics can be found in a classical paper of Jeffcott in 1919, in a place where it was more likely to be read by those interested in rotor dynamics. Jeffcott confirmed Foppel's prediction that a stable supercritical solution existed, and he extended Foppel's analysis by including external damping to the ground, and showed that phase of heavy spot varies continuously as the rotation rate passes through the critical speed. This is there is no evidence that Jeffcott was aware of Foppel's prior work. In fact, the Jeffcott paper does not contain a single reference. So, there is no way we can able to sure whether the Jeffcott was knowing the Foppel's work, the similar work by Foppel. So, this is a typical plot for a rotor. You can able to see this is the spin speed of the shaft as is increasing from from 15 to let us say 45 hertz, and this is the displacement. So, whenever the spin speed was close to the critical speed, there was high amplitude, and there was you can able to see the second plot is the phase plot. There is a change in the phase of around pi radians, and even at the second critical speed here there was change in the phase. We can appreciate Jeffcott's great contribution if we recall that a flexible shaft of negligible mass with a rigid disc at the midspan is called a Jeffcott rotor in rotor dynamics community. Sometimes it is also called the level Foppel Jeffcott rotor. The bearings are rigidly supported and viscous damping act to oppose absolute motion of the disc. This simplified model is also called the level rotor, named after D level. This is a diagram of a Jeffcott rotor in which there is a flexible rotor which is massless. This is a disc, rigid disc, and the bearings are rigid. They allow only the rotational motion of the shaft, and the disc is at the mid span of the shaft. So, this particular model is a Jeffcott model. In rotor dynamics, this Jeffcott rotor model is very popular, and we will see that this particular model can be used to predict various kind of phenomena in rotor dynamics, and this is a very famous and very important rotor model in a rotor dynamics, as we will see in the subsequent lectures. So, after Jeffcott, the publication, a lot of confusions which were there in calculation of the critical speed was clear, and then so many other development started, especially engineers, they started making high speed rotors, but they had some other problems. So, in the second phase of this review, we will see what are the various problems industrialists or they face, and then what was the other phenomena people could able to they could able to analyze. So, in this particular case, the second phase in which I will be starting from Skodala, he was from 1924 to Lund up to 1964. So, the development made in rotor dynamics up to the beginning of the 20th century are detailed in the masterpiece book written by Skodala. Among other things, his book includes the dynamics of elastic shaft with discs, the dynamics of continuous rotor without considering gyroscopic moment, the secondary resonance phenomena due to gravity effect, the balancing of rotors, which is very much practical importance, and methods of determining approximate values of critical speed of rotors with variable cross sections. He presented a graphical procedure to calculate critical speeds. which was widely used in industry. He showed that these supercritical solutions were stabilized by Coriolis acceleration. The ignorance constraint of these acceleration was the defect in Rankine's model. It is interesting to note that Rankine's model is a rational one for a rotor whose stiffness in one direction is much greater than its stiffness in the perpendicular direction. Indeed, it is now well known that such a rotor will have regions of divergence instability. It is less well known that Prandtl in 1918 was the first to study a Jeffcott rotor with a non-circular cross section. See the elastic asymmetry in the rotor. The Jeffcott's analytical model, the disc did not wobble because this particular phenomena was not occurring, because in the case of the Jeffcott rotor, the disc was at the mid span, and when the whirling was taking place, the disc was not having any tilting, and because of that it was not wobbling. So, this is the Jeffcott analytical model. The disc did not wobble. As a result, the angular velocity vector and the angular momentum vector were collinear and no gyroscopic moment were generated. So, you can able to see this is the Jeffcott rotor model in which the disc is at the mid span. So, during whirling, this disc will remain vertical, it will not tilt, because it is at the mid span, it should be tangent to the elastic line of the shaft. But in the second case, when the disc is slightly offset, then during whirling obviously this disc will tilt, and because it is spinning about its own axis and tilting about its diameter, there will be gyroscopic couple. So, these two cases you can able to expect that there will be a different natural frequency of the system because of this tilting motion, and because of this tilting motion there is a gyroscopic couple. There is another model, there is a cantilever beam. You can able to see this here. We have a point mass, this is spinning about its own axis with omega, and the whirling at nu, and this is another one in which there is a disc instead of a point mass and is spinning about its own axis with omega, and whirling, the whirling frequency is nu. So, we can expect that the figures C and D, they will be having different natural frequency, and they will be having different critical speeds because of gyroscopic moment, because here point mass is there. So, there will not be any gyroscopic moment, but here gyroscopic moment will be there. So, the restriction was removed by Scodola and others. The restriction of the Jeffcott rotor, in which the disc was at the middle, and because of that gyroscopic couple was not there. So, these researchers, they studied the effect of gyroscopic moment on natural frequency and critical speed. The gyroscopic moment has the effect of making the natural frequency dependent on the rotor speed. This is very important phenomena, and also not only it natural frequency depends upon the rotor speed, also it at the same time it doubling of their numbers, the natural frequency becomes twice. This we will see in subsequent plot, how the natural frequency become twice as compared to non-gyroscopic couple case. Along with other parameter, the ratio of diameter to polar moment of inertia play an important role in this particular gyroscopic effect. So, there is a famous diagram in rotor dynamics, that is called Campbell diagram. In this diagram is the horizontal axis is the spin speed of the shaft, vertical axis is the natural whirling frequency, and at 0 speed you can able to see that these are the first natural frequency, second natural frequency, third, fourth. several natural frequencies are there, and because in this particular case the gyroscopic couple has been considered. So, as we will increase the spin speed, the splitting of the natural frequency take place, and that they belong to forward world and backward world, and can able to see even this got splitted, and as we are going higher and higher, the splitting is more because of the gyroscopic couple, and especially when we are operating at high speed, these splittings are more. And this is the line which represent the 45-degree line, in which along this line the spin speed and the world frequencies are same, and wherever they are intersecting this natural frequency line, those are critical speed. This concept will be seeing in more detail as we will go into the subject. Okay. So, then about after the Jeffcott's analysis of around 1 decade later in 1933, the study of asymmetrical shaft system and asymmetrical rotor system began. These two rotor systems, we will see what are the difference between them. Like the former one are the system with a directional in the shaft stiffness. The symmetrical shaft system is in which there is a directional in the shaft stiffness. That means, the shaft stiffness changes with the direction as it rotates, and the latter one are those with a directional difference in the rotor inertia. With some figures we will see these two kind of asymmetry in the shaft system and rotor system. Like the two pole generator rotor and a propeller rotors are example of such system. Two pole generator system is example of asymmetrical shaft system, and propeller rotors are example of asymmetrical rotor system. As these directional difference rotate with the shaft, terms with time varying coefficients appear in the governing equation. These system therefore fall into the category of a parametrically excited system. So, let us see with the diagram what is two pole rotor. You can able to see this is a rotor for generator in which some slots are there for winding, and these are the holes for because of this shaft the stiffness in one of the plane will be less as compared to other one. To compensate that, some slots are made in other direction also, but still when such rotor rotates, you can expect there will be change in the stiffness with respect to time, and that gives parametric excitation to the system. And the Campbell diagram which we drew earlier, in which this was the spin speed, this was the world frequency, we will find that at a certain region there will be the natural frequency will be complex, and these are nothing but unstable zones. So, these analysis will study in subsequently during the study of instability in the rotors, and rotor will be very highly unstable in these regions. This is another example in which the rotor asymmetry is there. So, we can able to see as this propeller rotates about the fixed axis, their diametral mass moment of inertia would change, and because of that there will be rotor mass asymmetry. The most characteristic property of the asymmetrical system is the appearance of unstable vibrations, as we have seen in the Campbell diagram in the some rotational speed ranges. In 1933, Smith obtained a pioneer work in the form of simple formulation that predicted the threshold spin speed for supercritical instability varied with bearing stiffness and with the ratio of external to internal viscous damping. This was very simple formula which the Smith gave. The quote from the Smith's paper: the increase of dissymmetry of the bearing stiffness and in the intensity of external damping relative to the internal damping raises the threshold speed, and this threshold speed is always higher than either critical speed. The external in the rotor dynamics, there are two kind of damping we talk about. One is the external damping, another is the internal damping. External damping comes from the bearings, or there is if there is a interaction of the working fluid with the rotor, and internal damping is of the rotor material itself, because during whirling of the shaft there is a intermolecular interaction, and because of that there will be the tension compression of the rotor will take place, flexural vibration of the rotor will take place, and that will generate heat. So, there is internal damping. So, generally the internal damping gives instability, and but the external damping stabilizes that. So, that is the concept we are looking into. So, the formula for damping was obtained independently by Crandall in 1961, some 30 years later. Dick in 1948 also studied behavior of shaft having sections with unequal principal moduli. This system is stable provided you can able to see the first is the hysteretic damping, another is the viscous damping. This is the internal damping, and the second one is the external damping, and this is the formula by which we can able to predict the whirling the speed beyond which the system is unstable. So, if the speed is below this range, omega n is the natural frequency of the system, then the rotor system will be stable. If it crosses this particular speed, then there is a possibility of unstable region in the operating speed of the rotor. Just wait a minute. How much time? So, we are seeing that what are the problems which the rotor dynamics engineers were facing when the rotors were operating at high speed. One of the phenomena which we have seen due to the internal damping of the system, there were some regions of unstable operating speeds. So, now let us see some more such phenomena which were taking place because of various other reasons. So, as the rotational speed increased above the first critical speed, the huge amount of kinetic energy stored in the rigid body rotational mode of a high speed rotor is available to fuel a wide variety of possible self excited vibration mechanisms. However, the rotor dynamists' respite from the worrying about instability was brief. In the early 1920s, the supercritical instability in built up rotor was encountered, and shortly thereafter first shown by Newkirk in 1924 and Kimball to be a manifestation of a rotor internal damping, the damping between the rotor components, sometimes due to rubbing of the rotor component also this internal damping occurs. Then Newkirk and Taylor in 1925 described an instability caused by nonlinear action of the oil wedge in a journal bearing, which was named as oil whip. Baker in 1933 described self excited vibration due to contact between rotor and stator. So, this was another phenomena which Baker pointed out, that even due to rubbing between the stator and rotor there is a self excited vibration. Kapitsa pointed out that a flexible shaft could become unstable due to friction conditions in its sliding or bush bearing. This is a typical Campbell diagram in which this is the spin speed of the shaft, and this is the shaft, the natural frequency. You can able to see as this particular, I am correcting this again. This is a typical plot of run up or run down of a rotor system, in which this is the shaft whirl's frequency and this is the shaft rotational speed, and you can able to see this particular line as the rotor speed is increasing, the amplitude of vibrations which are indicated here are increasing up to this is the critical speed, but above critical speed then it diminishes. So, this is that is due to unbalance, this particular response will be occurring, only at critical speed it will be more, and these are the frequency component which is twice the rotational speed of the rotor, and generally it begins above the first critical speed. You can able to see this corresponding to the first critical speed, and here you can able to see that when this is corresponding to the first critical speed, and basically at this moment the rotor is actually rotating at twice the natural frequency, and the whirling is taking place at the natural frequency, and this particular phenomena is nothing but the oil whip. This we will study in more detail as we will go into the subject. So, this particular oil whip, when the shaft rotates at about twice the speed associated with the system, then it occurs. This is a typical experimental plot of the run up, and this is for run down for the similar thing. You can able to see that this is the corresponding to first critical speed. There is large oscillations here, and there are some subcritical phenomena is also observed in the first plot. Second plot is for run down, there more unstable regions are there. How much? 3. Okay. So, now let us see. What is the physically the instability in a rotor system is there. If rotor is if it is operating at an unstable region, so how its amplitude increases? Let us see through some animations. So, this is the plot in which you can able to see that this is the orbit of the shaft, and this is the x and y axis, and this is the orbit of the shaft as it rotates. And if the rotor is stable, if you give some disturbance, let us say we disturb the rotor here, after some time it will stabilize, again it will be having same orbit. Even if you take out the rotor position somewhere outside also, it will stabilize like this. But in an unstable case, once you disturb, the amplitude will grow gradually, and then failure will be taking place. So, this is an unstable region. So, let us see some animations. This is a perfectly steady state shaft orbit. Now, let us see a stable rotor, but we have given some disturbance. So, after some time again it comes to its original orbit. There is another, we have given disturbance outside and is coming to the actual orbital. So, this is a stable system. This is an unstable system. Once we disturb it, the amplitude increases. You can able to see. Sometime the Campbell diagram, along with the frequency, we add the logarithmic decrements, and the sign of the logarithmic decrement determines whether the system is stable or unstable. So, generally whenever it is negative, the system is stable. If they are positive, they are unstable. So, with this we can able to see various modes. So, like this is the first mode, second mode, which are stable, which are unstable, after what speed they are stable, we can able to study. Today in this particular lecture, we started with some introduction to the rotor, and even some basic phenomena we have seen. We started with the history of the rotor dynamics, in which the first published work in this particular field was in 1869 by Rankine, but there was some flaw in those in that particular paper, and that discouraged the development of high speed rotors for almost 50 years, but the test rig during this period were made and they were operated above the critical speed, which were against the predictions of the Rankine. So, in 1919, Jeffcott clarified this confusion, and he gave a very basic model for prediction of the response, unbalanced response above the critical speed, and he said that it is possible to rotate the rotor at above the critical speed, and because of that, development of the high speed rotor began, but that led to the problem of other kind of unstable behavior of the rotor, and people then started working on finding the solutions for those instability. We will continue this particular the history of the rotor dynamics and the state of the art of the rotor dynamics in the subsequent lecture.